Welcome to Maths with EJD. In this video, we'll be talking about applications of second order ordinary differential equations. We have seen a lot of things about second order ordinary differential equations already. So we've seen the fact that we can broadly classify them into homogeneous, homogeneous, and non-homogeneous. Okay. So um so they can be we can have homogeneous equations and we can also have non-homogeneous equations. And of course, to solve homogeneous equations, we saw that we could use the characteristic equation method. Characteristic equation method. Okay, we saw that already. And here too, um, so the non-homogeneous equation has two parts. The first part is the complementary part where we get the complementary function, and that uses the same, that uses the characteristic equation method still, characteristic equation method. But then we also have a particular solution, uh, which takes into account the external forcing, which makes the equation non-homogeneous. And here we saw methods like undetermined coefficients. We saw um, the operator technique, the operator method of solution. And we also saw um, what we know as variation of parameters, variation of parameters. Okay. All right. With all this in place now, we are here to see some applications of second order ordinary differential equations. So our focus shifts to applications. Applications, you know, of second order ODs. Okay. Second order ordinary differential equations, ODEs, appear in various fields, including physics, engineering, biology, and economics. These equations describe systems where the rate of change of a quantity depends on both the quantity itself and its first derivative, okay? Because it goes all the way to the second order. So I'll just list these things. We have the first one, which is the mechanic. We talk about in mechanical systems. In mechanical systems, um, where we have the Newton's second law of motion. Okay. Um, so Newton's second law states that force equals mass times acceleration. That's F equals ma. This is a standard law from Newton. And we have a very good example of this, We have an example of this. I guess I want to go this other way. Um, we have an example of this with simple harmonic motion. Simple harmonic motion, which talks about looking at the mass spring system, for instance, mass spring system. Okay. So here, a mass M, a mass M attached to a spring, okay, follows what we know as Hooke's law, and that gives us m d squared x d t squared plus kx equals 0. So we have displacement there and all of those things, as we're going to see pretty soon. Of course, you can also write this as m x dot 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 tells you that it is time dependent, and that it is of second order. plus kx equals 0. So that is Hooke's law right there for you. So here we see that x of t is the displacement. X of t is the displacement of the mass. Displacement of the mass. That is this x, which is a function of time now. And then we also have k. K is the spring constant. K is the spring constant. Now, interestingly, if when you solve this equation, right, you get the solution. You get the solution to that equation, which is, looking at that, of course, you can use all the laws we've been talking about all along. So the solution is x of t equals a cos omega t. So obviously, you're going to get some uh, complex results. So a cos omega t plus b sine omega t, that's the solution to that problem. But then omega has a definition that so it's where omega is equal to where omega is equal to square root of k over m, that constant over the mass of the spring, right? So that's one application talking about mechanical systems. Then we also have applications for this in electrical circuits, um, electrical. Okay, we have it in electrical circuits. Okay, so in electrical engineering, circuits with resistors, we have resistors, R, inductors, L, and capacitors. And capacitors, C, can be modeled using second order ODEs based on Kirchhoff's voltage law. Okay, so a very good example is the series RLC circuit. Okay, so here applying Kirchhoff's law, applying Kirchhoff's law to a series RLC circuit gives L d squared Q dt squared plus R dq dt plus Q over C equals 0. And like I said before, because it is time dependent, you could actually write it as LQ dot dot. So dot dot tells you it's dependent on time, and R Q dot plus Q over C equals 0. So this is the RLC circuit under Kirchhoff's law. So here now, is the Q of T is the charge rather, is the charge on the capacitor. So Q is charge on the capacitor. Then we have L to be the inductance. L is the inductance coming from an inductor. Then we have R is the resistance coming from a resistor, is the resistance. Okay. And then we have the capacitance coming from a capacitor. So C is the capacitance. Okay. So we see that this equation describes damped oscillations, damped oscillations, all right, of charge and current in the circuit. Okay. So you can try to solve this using all the methods we know, using relevant methods that we've been working with. So we actually have this in structural engineering too. So we've seen it in mechanical systems. Now we've seen it in electrical circuits. Now you can also have it in structural engineering, where you deal with beams, where you deal with beam deflection. So vibrations are involved, right? Beam deflection. Okay. So The bending of beams under a load is governed by second order ODs derived from, okay, let me just write this. The bending of beams, the bending of beams, like in bridges and buildings under a load is governed by second order ODs derived from Euler, Bernoulli. So you see Euler and Bernoulli, they are here again. Euler, Bernoulli beam theory. Okay. So example, like we said, we can have that in the deflection of a beam. Deflection of a beam. Okay. So for a beam subjected to a distributed load, Q of X, the equation governing its deflection, governing its deflection, y of x is EI d squared y dx squared equals Q of x. Of course, if you want to write it in the shorthand form I've been writing, so this is like EI y. So this is EI y prime prime equals Q of x. Okay. So prime prime says space. Like I think I've said that before, that when you have y prime prime, that's like d squared y, the x squared. Or when you have y dot dot, that's like d squared y, the t squared. So it's time dependent. That's the standard notation. I mean, it doesn't really matter because in some cases too, you can see some y prime prime being you know, time dependent. So it all depends on who is using it. Okay. So of course, back to this now, y prime prime equals Q of x. And here we have E as the Young modulus. E is the Young's modulus. Okay. And then you have I, which is the moment of inertia, moment of inertia of the beam's cross section, of the beam's cross section. Of course, remember that inertia is the reluctance to motion when a body is at rest, or reluctance to come to rest when a body is in motion. So that reluctance is captured in moment of inertia in a beam. So this equation helps engineers design safe and efficient, structures like bridges and skyscrapers. So you have a lot of maths to thank for safety in buildings, skyscrapers. Okay. Okay, number 4, we have fluid dynamics. You can also see second order the ordinary differential equation in fluid dynamics, where we talk about things like damped motion fluids, damped motion, damped motion in fluids, right? So objects moving through a fluid experience resistive forces proportional to velocity, leading to second order ODs. So objects moving through a fluid experience resistive forces proportional to velocity, leading to second order ODEs. Okay. So a good example would be free falling object, free falling object with air resistance. Okay. So here we see that Newton's second law, Newton's second law for an object, falling under gravity with air resistance, gives m d squared y dt squared equals mg minus k dy dt. Okay, so if you want to write it in my usual form, that's like my tt equals mg minus ky dot. My dot dot, right, equals mg minus ky dot. Okay, that is a free falling object under gravity. And here for sure, we have K is the drag coefficient. So as the name implies, there's a bit of drag in the air as it is falling, the drag coefficient. And then you have Y of T. So I think that will be analogous to the moment of inertia in the other situation we considered the other time. K, this is M, right? So M, and then this is M, okay? So Y of T is the height of the object, okay? And then these models, real world, real world falling objects, such as parachutes for safety in aeroplanes and all that. Okay, number 5, I guess it's the last. Number 5, we have population dynamics. In population dynamics, we have second order differential equations, population dynamics. So like when we talk about logistic growth with time delay, You know, we've seen exponential growth, which is growth under ideal situation, which never really exists. You know, that is growth with unlimited resources and unlimited space. But logistic growth makes population growth a bit more realistic because there's usually no unlimited resources and no unlimited space, right? So, and this is a biological angle to the thing. So in biology, population models population models with constraints on resources often involve second order ODs. Okay. For example, we have what we call the predator prey dynamics. And a very popular equation for this is the Lotka-Volterra model, model. Okay. So here we have a simplified second order model for a predator. Usually it's a system of equations which we're still going to talk about system of ordinary differential equations as we go on. So a simplified second order model for a predator prey system. Okay. So this is like just one representation. So you have d squared p dt squared plus a dp dt plus bp equals 0. Okay. So you can write it in my form, that is P dot dot plus AP dot plus BP equals 0. So this is the simplified form of the predator prey, and this represents um so this actually helps, right? This helps in ecological conservation, in ecological conservation and fisheries management and fisheries management. Okay. So these are some examples. Of course, we can keep going. So in conclusion, we see that second order ODEs play a crucial role in various real-world applications from mechanical vibrations and electrical circuits to population dynamics and fluid mechanics. By solving these equations, we can gain insight into the behavior of physical systems and can predict their future states. So that brings us to the end of second order ordinary differential equations. So going forward, I think we'll be talking about higher order or something like that. So watch out. I'm still going to talk about Laplace transforms. I'm still going to talk about systems of ordinary differential equations. So it's going to be an exciting journey. So come along. If you have not subscribed to this channel, you'll be missing out. So please go ahead and subscribe. And if you have subscribed already and you've forgotten to hit the notification bell, please, everybody who wants to subscribe, hit the notification bell so you can always get alerted each time a new video is released so that you don't miss out on anything. All right, then let me know in the comment section how helpful these videos are for you, and if you like me to teach a topic or solve a problem, I can also do that. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.